All right, welcome everybody to our last chapter of the course. This is chapter 11 on what's called intermolecular forces. These are the forces between different molecules. So we've spent a lot of time in the course talking about intramolecular forces, the forces within a molecule, i.e. bonding, right? But now we're going to be talking about forces within different molecules, between different molecules. And that will give rise to a lot of the physical properties and chemical properties of substances, okay? And so, first, just to remind you, right, hopefully you know that this is a solid, liquid, and gas, or at least schematics of them. And you remember that, you freeze or melt to go between a solid and liquid, and you evaporate, boil to go from liquid to gas, and you condense a gas to go from gas to liquid. And so intermolecular forces, why are some substances solids, others are liquids and gases? We'll be able to answer that. What makes a substance sticky? Why is a gecko's foot, so amazingly sticky? What changes the boiling points of substances? How can we do that? And so again, difference between intermolecular forces, which I'm abbreviating as IMF, and intramolecular forces. Think of an interstate. That's a highway that goes between states, right? So that's intermolecular forces, means the attractive interactions between particles, which determine their physical properties in a lot of cases. Intra is within. Intramolecular forces are bonding. Is it ionic, covalent, the shape? Intracellular means within a cell. Okay, things that we've talked about already, intramolecular forces. So states of matter depend upon IMFs. In a gas, you don't really have strong intermolecular forces. Remember, the ideal gas law actually said, we didn't state it this way, but said there was no intermolecular forces. We said that according to kinetic molecular theory, the particles between different gas molecules weren't interacting at all. Now we know that that's actually an approximation. It's a pretty good approximation, but at high pressures, for example, there are significant intermolecular forces, or at low temperatures between gases. And there was a special equation that I briefly introduced called the van der Waals equations that actually took into account the intermolecular forces, the attractive nature between gas particles. It's very weak, but it does exist. So I put not important on the slide. Liquids, are obviously a lot closer together. They're flowing over one another. The molecules are. And so I put somewhat important. Intermolecular forces are somewhat important. And in a solid, it's a relatively rigid structure. Atoms are still moving. Molecules are still moving in the solid. They're vibrating. But they're relatively, they're staying in place. Okay, so really intermolecular forces are quite strong here and very important. We're going to be talking about three main types of intermolecular forces: the London dispersion forces, the dipole-dipole forces, and hydrogen bonding interactions. All molecules have what are called London dispersion forces. Only polar molecules, i.e. those with a dipole, have a dipole-dipole forces, and only molecules with hydrogen, specifically hydrogen bonded to the three most electronegative elements, nitrogen, oxygen, fluorine, have hydrogen bonding intermolecular forces. So we'll go through these one by one. And the general van der Waals the equation that we talked about for gases, van der Waals came up with a lot of these ideas of intermolecular forces. And so we refer to all three of these intermolecular forces as a big umbrella, a big inclusive term, as van der Waals forces. So if you hear me say van der Waals forces, I probably won't say it, but van der Waals forces means intermolecular forces. And a London dispersion is just a type of van der Waals force. A dipole-dipole force is just a type of van der Waals force. It's a type of intermolecular force, okay? And so that's sort of just an introduction to intermolecular forces.